infinite universe is here with new interesting story of star. Right in front of you is one of the fastest and most extreme objects in the universe. It spins far quicker than the blades of a helicopter, hundreds of times faster, in fact. Its mass is enormous, nearly 2.5 times greater than our Sun. Despite this, it's not very big in size. If you were to place it on Earth, it could fit comfortably inside the borders of New York City. This remarkable object is pulsar J0952J0607, the heaviest neutron star ever discovered. This pulsar rotates an incredible 707 times every second. That's faster than the blades in your kitchen blender or even the turbines of a jet engine. But how does something so massive spin so fast? It needs an energy source, and this pulsar has one, a white dwarf. A white dwarf is what's left after a star burns out. In this case, the white dwarf is caught in the strong gravitational field of the pulsar. It's so close that its matter is being stripped away by the pulsar's gravity and turned into a superheated stream of plasma. This plasma flows toward the pulsar, which absorbs it, gaining even more energy. As it takes in this matter, the pulsar spins even faster and emits stronger radiation. But this process is not without risk. The pulsar keeps getting heavier as it absorbs the white dwarf. If it gains too much mass beyond a certain point, it won't be able to hold itself together. The force of its own gravity will crush it further, and it will collapse into a black hole. Neutron stars, like this pulsar, are among the strangest objects in the universe. They are formed when very large stars, at least 8 times bigger than the Sun, run out of fuel. Once the star can no longer support itself, its core collapses at incredible speed, heating up to billions of degrees. The outer layers of the star expand and cool, becoming a red giant. Eventually, the collapse results in a powerful explosion called a supernova. What remains after the explosion is the dense core, a neutron star. Most neutron stars have a mass about 1.4 times that of the Sun, but their size is tiny in comparison. Their radius is only about 6 to 7.5 miles. To put this in perspective, the Sun is nearly 870,000 miles in diameter, while a neutron star is just over 6 miles wide. This compression makes the matter inside incredibly dense. NASA estimates that just 1 teaspoon of neutron star material would weigh about 1 billion tons on Earth. That's about the same as the weight of 3,000 Empire State Buildings or the combined weight of all humans on the planet. This extreme density means that if you dropped even a small piece of neutron star material onto Earth, it would blast through any surface, drilling down through the ground all the way to the planet's core. Everything around us, in comparison, is almost weightless. Neutron stars also have extremely high temperatures. Their surface temperatures can reach between 600,000 to 1 million degrees Celsius, and right after they are formed, they can be as hot as 10 million degrees, about 1,800 times hotter than the Sun's surface. Despite this heat, the surface remains solid and is believed to be covered by a thick iron crust. What lies beneath that crust is still a mystery. Scientists think that under such pressure and temperature, the basic particles in atoms, protons and neutrons, might break down into even smaller particles called quarks. If that's true, the core could be filled with a bizarre substance known as quark matter. Another mind-blowing feature of neutron stars is their gravity. It's so intense that even the Sun's gravitational pull is weak by comparison. If a spaceship landed on a neutron star and wanted to take off, it would need to reach speeds close to 93,000 meters per second, nearly half the speed of light. In contrast, escaping the Sun's gravity only requires about 383 meters per second. Dropping an object as light as a pound on a neutron star would create an explosion equal to thousands of hydrogen bombs. Only black holes have stronger gravitational pull than neutron stars. Neutron stars come in many types. Some are so unusual that scientists once mistook them for alien signals. In 1967, British scientists noticed strange, perfectly timed signals coming from space. It was so precise that some thought it could be a message from intelligent life. However, these signals were eventually found to come from a special kind of neutron star called a pulsar. These stars spin and emit beams of energy from their magnetic poles. As they rotate, these beams sweep through space like a lighthouse, sending bursts of radiation toward Earth that we detect as regular pulses. Pulsars rotate incredibly fast because of a law called the conservation of angular momentum. You can understand this by imagining a figure skater spinning. When they pull their arms in, they spin faster. The same thing happens to a collapsing star. As it shrinks, it spins faster and faster. Most neutron stars slow down over time, but some, like pulsar J0952J0607, stay fast because they keep pulling in matter from a companion star. This added matter boosts their spin rate, making them incredibly fast pulsars. When pulsars spin, their magnetic fields send out beams of radio waves, light, X-rays, and gamma rays. These beams can be detected on Earth and are so precise that pulsars are sometimes used like cosmic clocks. Some pulsars are so consistent that they're more accurate than atomic clocks. It's hard to imagine something just over 6 miles across spinning hundreds of times every second, but that's what happens. Among all known pulsars, PSR J0952J0607 stands out as the fastest and heaviest. While most neutron stars have a mass of about 1.4 times that of the Sun, this one has nearly 2.4 times the Sun's mass, getting dangerously close to the limit where it would collapse into a black hole. Normally, a neutron star spinning slowly would collapse if it reached just above 2 solar masses. But because this one spins so fast, it resists collapse, at least for now. It gets its speed and mass from a white dwarf companion, which it is slowly destroying by pulling in its material. This kind of pulsar is often called a black widow because it consumes its partner. If this pulsar somehow entered our solar system, say orbiting near Mars or Jupiter, it would be catastrophic. The nearest planet would be torn apart by its gravity. Other planets would be thrown out of orbit. Earth's atmosphere would vanish instantly, and the planet would become a scorched wasteland. Eventually, even the Sun would be pulled in and destroyed. When the pulsar reached 3 solar masses, it would collapse into a black hole, ending what's left of the solar system. But PSR J0952J0607 isn't the only extreme object in space. There's another, much closer, just 1,000 light-years away, called Vela. It's one of the brightest pulsars ever discovered and one of the closest to Earth. It recently released the most powerful burst of light ever seen. Its gamma radiation is 200 times stronger than typical pulsars. This suggests something strange is happening within its energy beams, which stretch almost a full light-year into space. Scientists think this might be caused by powerful magnetic fields or unusual acceleration zones beyond the pulsar's surface. NASA recorded the sounds of Vela's radio pulses and converted them into sound. It resembles the thumping of helicopter blades or a car engine. Vela's magnetic field is also incredibly strong, about 2 trillion times stronger than Earth's. But there are even more extreme stars with magnetic fields 1,000 times stronger. These are called magnetars. Only 1 in every 10 supernovae produces a magnetar. They are the most powerful magnetic objects in the universe. Magnetars can release bursts of X-rays and gamma rays that are unimaginably powerful. Their magnetic fields are so intense that they cause the star to quake, cracking its surface and releasing huge amounts of energy. If a magnetar had a starquake within 4,000 to 6,000 light-years of Earth, it could damage our atmosphere. You might first notice electrical blackouts or GPS problems. If one came even closer, the consequences would be far worse. Now imagine if a magnetar took the place of our Sun. It would look like a tiny sphere just 8 millimeters wide but with 1.5 times the Sun's mass. You wouldn't even realize the Sun had changed, your death would be instant. Its magnetic field would rip apart Earth's atmosphere and break down all matter. Mercury would be destroyed first, followed by Venus, Earth, and Mars. Even Jupiter might not survive unless the magnetar's energy ran out quickly. Fortunately, magnetars don't last long, just around 10,000 years. In contrast, pulsars can live for billions of years. That gives them time to do some surprising things like form planetary systems. For example, PSR B1257+12 has 3 planets, each several times heavier than Earth. Another pulsar, PSR J2007+3120, has 2 planets that orbit it every couple of years. This is extremely rare. Only about 0.5% of known pulsars have planets. These planets might have formed from material left over from the star's explosion or from a companion star. They might even be planets that were captured by the pulsar's gravity. No matter how they formed, these planets live in extreme conditions. If there's life there, it would be under constant radiation. These systems are dangerous and chaotic, unlike the calm circular orbits we see in our solar system. But their existence shows how strange and surprising the universe can be. While you were reading this, more than 100 supernovae happened across the universe, some leaving behind neutron stars, others creating black holes. The universe continues to change, evolve, and astonish us, and there's still so much left to discover. Imagine our sun as just a small pebble in the vastness of the universe. Now, imagine something even more incredible, a star that contains a black hole inside it. This might sound impossible, but scientists have discovered signs of such ancient stars, and it's leaving everyone amazed. These strange cosmic objects are not only a mystery, but they might also help us understand how the universe came to be what it is today. But how can a black hole actually exist inside a star? That's the question scientists are trying to answer. Stars are like cosmic factories. In their superhot cores, they produce most of the elements that make up everything in the universe. The stars we see today work in a certain way, but the stars that existed at the very beginning of time were very different. Some of them didn't have the usual kind of core. Instead, they had black holes in their centers, which helped them grow bigger than anything we can imagine. To understand how these stars work, let's first look at how a normal star forms. A star is born when a huge cloud of gas and dust in space starts to collapse under its own gravity. The center of the cloud heats up as more material gathers, forming what scientists call a protostar. This is the earliest stage in a star's life. As it continues to pull in gas and dust from its surroundings, the protostar eventually gathers enough material to start nuclear fusion, the process that powers stars. When this happens, the star becomes what we call a main sequence star, just like our sun. For the sun, it took around 50 million years to reach this phase. Most stars spend the majority of their lives as main sequence stars. But eventually, they run out of hydrogen, the fuel that keeps them shining. What happens next depends on how big the star is. Smaller stars like our sun will become red giants and then shrink into white dwarfs. These white dwarfs are very small, but they're incredibly dense, about 200,000 times denser than Earth, even though they're similar in size. Over billions of years, the white dwarf cools down and eventually turns into a solid crystal, made of carbon and oxygen, kind of like how water turns into ice. However, stars that are much bigger, over 10 times the mass of our sun, go through a different process. After they run out of fuel, they explode in a massive event called a supernova. If the star is massive enough, the core collapses and becomes either a neutron star or a black hole. Neutron stars are already incredibly dense. They're only about 12 miles across, but they have the same mass as our sun. Just a sugar cube-sized amount of material from a neutron star would weigh 1 billion tons, about as much as a large mountain on Earth. But if a star is even more massive, the gravitational collapse becomes so powerful that nothing can stop it from shrinking into a black hole. While the star is still burning, there are two main forces keeping it stable: the outward pressure from nuclear fusion and the inward pull from its own gravity. Once the fuel is gone, fusion stops, and gravity wins. The star collapses into itself, creating a black hole, just like how a building might collapse during a controlled demolition. Albert Einstein once said that anything could become a black hole if enough mass was packed into a small enough space. Once a black hole forms, it starts to grow by pulling in more and more material. The area around it, where gravity is so strong that nothing, not even light, can escape, is called the event horizon. As the black hole consumes nearby matter, the event horizon expands, allowing it to eat even more. However, there's a limit to how fast a black hole can grow. This is called the Eddington limit. It's kind of like trying to fill a balloon with air. If the balloon has tiny holes, the pressure will eventually push some air back out. Similarly, when too much material falls into a black hole too quickly, it creates radiation so powerful that it pushes some of the incoming matter away. When matter spirals into a spinning black hole, it forms a disk that rotates extremely fast. Some of this matter turns into energy, up to 42% of it, in fact. This is far more efficient than the energy produced by nuclear fusion in stars. Imagine a future where humans could somehow harness this energy. It would be a game changer. Even the largest black holes in the centers of galaxies, called supermassive black holes, face the same limit. Yet, many of them are far larger than we ever thought possible. This raises a big question: how did they get so huge so quickly? Regular black holes growing over billions of years can't explain it. So, scientists came up with a fascinating idea: quasistars, also known as black hole stars. These quasistars may have been the biggest stars to ever exist, possibly larger than any black hole we know today. They formed when the universe was still young, during a time when massive gas clouds filled space. These clouds collapsed under their own gravity, forming huge stars. Some scientists believe these stars may have started forming inside halos of dark matter, mysterious, invisible material that holds galaxies together. These halos could have had up to 100 million times the mass of our Sun. Now, most large stars eventually explode in a supernova, leaving behind a black hole. But quasistars were so enormous that instead of exploding, their cores collapsed quietly. A small black hole formed at the center, but instead of tearing the star apart, the outer layers stayed intact. From the outside, the star looked normal. But inside, a baby black hole was slowly eating it from within. This baby black hole began spinning and formed a disk of hot gas around it, spinning at nearly the speed of light. Since the gas was falling straight into the black hole, there was no limit on how fast it could grow. The disk became hotter and hotter, releasing powerful radiation that made the entire star shine like a small galaxy. These quasistars grew at a rate we've never seen before. In just a few million years, a short time by cosmic standards, they could become bigger than anything we know. Some might have even grown to be as large as the entire solar system. That includes stars like UY Scuti and Stephenson 2-18, which are among the biggest known stars, and black holes like TON 618, one of the most massive ever discovered. But with great size comes a short life. Unlike our Sun, which has a lifespan of about 10 billion years, quasistars burned bright and died young. After just a few million years, they exploded in a spectacular burst, leaving behind a massive black hole. These black holes then wandered through the universe, devouring anything in their path. Now imagine one of these ancient monsters entering our solar system. The gravitational pull would throw everything into chaos. Planets would be pulled out of orbit. Asteroids would rain down on Earth. Temperatures would rise, and life as we know it would end long before the quasistar reached us. Eventually, it would swallow Earth too. Although there are probably no quasistars left in the universe today, their central black holes may still be around. These black holes could have acted as seeds for the supermassive black holes we now find at the centers of galaxies. In fact, quasistars might have played an even bigger role in shaping the universe. Their collapses could have sent out powerful gravitational waves, rippling through space and helping form the structures we see in the universe today. Quasistars might have also influenced the possibility of life. The intense radiation from these giant stars could have made nearby planets uninhabitable or maybe even helped create the right conditions for life in unexpected ways. Either way, they were incredibly important in the early stages of the universe. Here's something even more mind-blowing: there might still be tiny black holes floating around from the beginning of time. These are called primordial black holes, and they could be the size of an asteroid but have huge masses. Some scientists think they might have become trapped inside gas clouds that later turned into stars. That means a star like our Sun could possibly have a small black hole hidden in its core. Stephen Hawking once suggested that if the Sun had a black hole inside it with the same mass as Mercury, we wouldn't even notice it. While this idea is unlikely, it's not impossible. Scientists think that if a star did contain a primordial black hole, it would behave differently from normal stars. These stars, sometimes called Hawking stars, would be a little cooler than usual and might expand differently as they age. Researchers have already found around 500 red giants that are cooler than they should be. To test their theory, scientists are studying the way these stars vibrate. If the vibrations are unusual, it could be a clue that they hide black holes inside. Some scientists even believe that the mysterious dark matter, which makes up most of the mass in the universe, might actually be made up of countless tiny primordial black holes. If there are enough of them, then surely some have ended up inside stars. Thanks for watching. Like and subscribe our channel. Have a good day.